Thank you, Roberto. Good morning, everyone. And as we get settled in, what better topic to begin the day than ultrasound physics? Listen, it's a pretty scary part of the exam, especially for the first-time takers. Fortunately, for those recertifying, there's much less physics on that part of it. But there's no person in the world who's a better lecturer on ultrasound physics than Dr. Sidney Edelman. I won't lie to you, 20 years ago, I think he was involved in this course, and the handout that he's given you is really priceless. You need to look at that handout, memorize everything in it, because the questions from the boards will come from that. Now, his lecture today is slightly different than the handout. His livelihood, his whole world really depends on keeping the secrets that he knows and then, giving lectures and traveling and teaching us all about ultrasound physics. So he cannot give you everything that he has in his lecture in the handout. But what he has given you is really the key to the kingdom as far as ultrasound physics goes in the exam. I would also tell you that he's published a textbook. I've purchased the 4th and 5th edition. I get no royalties, trust me. And it's really a very readable book. So if you want to do a deeper dive into ultrasound physics, you can certainly do that. And without further ado, I'll introduce really the world's expert on ultrasound physics, Dr. Sidney Edelman.
That's quite an introduction. I have to say that it really isn't as special as it seems. I'm reminded of two things. First, when I was a young man at the Texas Heart Institute, I started my professional career designing VADs and artificial hearts at the Texas Heart Institute with Dr. Cooley. And Dr. Cooley would do valve surgery and bypass surgery at the same time in the same setting, and sometimes he would do the valve first and sometimes he would do the bypass first. So we were sitting around late one day and I said, Dr. Cooley, how do you decide what to do? And he said, well, Sid, you always do the worst first. Well, here we are, okay? And the other thing is my dad, who is a brilliant man, always told me how to be successful. He said, exceed people's expectations. He said, it's not whether you do a good job or not. I said, okay. He said, so son, my suggestion is pick something where people have very low expectation. So what we're going to do is take care of the physics. I have an easy job. The only thing I have to do for the first-time takers principally is to prevent you from bleeding to death on the physics portion. If you get an average grade on the physics, and then you take care of your clinical material based on the brilliant people in this faculty and your clinical training, you'll be fine. So we're not going to dive into everything and worry about every last point in physics, but we'll certainly push physics off the table. So let's start. Start off with physics at the speed of light. Those of us that were Boy Scouts or Girl Scouts remember that you could tell the distance from a storm based on the time between the flash of lightning and the clap of thunder. And the reason is because light travels at 200,000 miles per second and sound travels at 1/5 of a mile per second. So this really isn't, sound doesn't travel very fast, so we have to teach it at the speed of light. So let's accelerate through it. Essentially, what is sound? Sound is a wave, and the purpose of all waves, is to carry energy, not matter, from place to place. Sound in particular is created by a vibrating object, and what happens is when the tines of this tuning fork vibrate, they squeeze molecules together and then they stretch them apart. Compressions and rarefactions. And that's the definition of sound, a series of compressions and rarefactions. Now, since we need molecules to compress and rarefy, sound, unlike other waves, cannot travel through a vacuum. It has to travel through a medium. Electromagnetic waves, light waves, they can travel through a vacuum, but not sound. Sound can only travel through a medium. Sound is a mechanical wave, which means the molecules actually move, and it's something called longitudinal. So let's define those things. But our first job is this. Let's say a wave goes by, and we say, there's a wave. Now, there are all kinds of different waves, right? There are light waves, there are heat waves, there are sound waves. How do we identify the subset of waves that are sound waves? By what is rhythmically varying. And if what is rhythmically varying is called an acoustic variable, then that wave is indeed a sound wave. And there are 3 acoustic variables. They are pressure, which is the concentration of force over an area, density, the concentration of mass in a weight, and distance. And if any of those 3 things rhythmically vary, then we have a sound wave. One thing to note, of course, we measure pressure in millimeters of mercury. The scientists, the physicists use a rather atypical unit called the Pascal. Now, we would say if we have pressure or density or particle motion rhythmically varying, then we have a sound wave. Actually, when one varies, all of them vary. So this is the description of a transverse wave. What do we have? We have a wave that is propagating from the right side of the screen to the left side of the screen, and the blue diamond in the wave, a particle in the wave, is moving in a direction that is perpendicular to the direction of propagation. This is a transverse wave. Now, there's the other kind of wave, which is a longitudinal wave. In a longitudinal wave, the particles in the wave move back and forth and back and forth and back and forth along in the same direction that the wave is propagating. Along, long, longitudinal. So this brings us to the first big lie in ultrasound physics. Every time you see a wave drawn in any notebook, any text, any slide, sound is always drawn as if it's transverse. It's not. Sound is longitudinal. The reason why we draw them as if they're transverse, it's the only way to label them and have them make sense. But audiophiles know this already. You know, if someone owns a speaker, which is a radical thought, you know, a speaker, the movement of the cone of a speaker is in and out in a piston-like motion, which compresses air molecules and rarefies air molecules and creates a wave. And that wave is indeed longitudinal. And where the molecules are squeezed together, we have the compression, regions of high density and high pressure. Where the molecules are stretched apart, we have the rarefactions, regions of low density and low pressure. And sound is simply a series of compressions and rarefactions. All right, so now we have successfully identified a wave as a sound wave. So you're now going to tell me, describe it to me. I want to know what it's like. So there are 7 parameters that describe sound. Here they are: period and frequency, amplitude, power, intensity, wavelength, and speed. Now this bizarre architecture has a reason. This architecture will allow you to look at this stuff in later days and remember what we're supposed to do. So we're going to see this again. So the first parameter that we're going to talk about is period. If you remember way back to high school, a period was like 40 minutes or 45 minutes or 50 minutes. It was the time that it took to complete one class. In ultrasound physics, it's the time that it takes to complete one cycle, as identified by the red arrow, the double-sided red arrow. Now, it has units of time. In this case, it has units of microseconds, millionths of seconds. So a period is very short in diagnostic ultrasound, ranging from about 0.06 to 0.5 microseconds, less than a millionth of a second. Now, the period is determined by the ultrasound machine, by the sound source, and we cannot change it. It is what it is. So that's what we need to know about period. Now, what about frequency? Frequency asks and answers questions like, how many meals do we eat a day? 2 per day, 3 per day, something like that. It really is the number of certain events that occur in a particular time. And the time is 1 second. And in this case, the event is the cycle. So if way out here is 1 second, what's the frequency of this wave? Well, it is 1, 2, 3, 4.5. 4.5 per second. Another way to say that is 4.5 hertz. Now, sometimes I say things that are very, very simple, and I'm not trying to insult you. I just want to make things a little bit more clear for you, because sometimes we stub our toe. There is a habit to see the word hertz and to say, oh, that's cycles per second. That doesn't serve us. Let's separate hertz into 2 parts. First part, how many are there? And the second thing is, what is the event? Well, in this case, how many are there? 4.5. What's the event? The cycle. Later on, we'll be talking about frame rate. And we may say the number of images a machine creates in a second. We may say that the frame rate is 120 hertz. How many are there? 120. What's the event? Pictures. We could talk about heart rate. Frequency is about 1.2 hertz. How many per second? 1.2. What's the event? Cardiac contractions. If you do that, you'll stay out of trouble. And there's a reason why I'm telling you that. You'll see that in a little bit. Okay. So frequency, and you know what? Frequency doesn't even exist. Frequency does not exist. You know, we say, oh, we have a transducer that has a frequency of 6 megahertz. That's 6 million cycles per second. There is no way a transducer puts out 6 million cycles per second. Why? Because it listens like 99.9% of the time. So frequency is a construct. It's the reciprocal of the period. And the reason why it's used is the range of periods from 0.06 to 0.5 microseconds equates to differences in frequency from 2 megahertz to 15 megahertz. So by using frequency, it gives us a nice broad range. You know, we're not going to sit there and say, oh, the frequency changed from 0.06 microseconds to 0.0605 microseconds, and people aren't going to go, ooh, that's a big change. But if we say the frequency changed from 2 megahertz to 4 megahertz, that's real. So frequency is simply a construct. We can't change that either. Now, people sometimes say, you know, yeah, we can change the frequency. I have knobs. I can change my transducer. Well, first of all, changing your transducer is cheating. We're not talking about the same system. Then, can you change the frequency of sound coming out of an object? The answer is not really. Not the natural frequency at which an object rings. You know, if you whack a gong, it rings at a particular frequency. And it is what it is, and you can't change it. So frequency is sort of fixed. Okay, frequency is reciprocal. Frequency affects penetration and image quality. We'll talk about that later. Now that we know frequency, it gives us the ability to define ultrasound. Ultrasound is a frequency so high that man can't hear it. It's defined by the physiology of the human ear. Any frequency higher than 20,000 hertz is ultrasound. Audible sound, the frequency between 20 hertz and 20,000 hertz, that's audible. And infrasound, any wave with a frequency less than 20 hertz. Now, you'll never get a question on the boards about a frequency of 20,000 cycles per second. They're not going to do that. But there may be a creative way of writing questions where they say, which of the following is ultrasonic and least useful in clinical cardiac ultrasound? Well, then we know we have to pick a number that's greater than 20,000, and it probably should be less than 2 million. You know, so an example, 50,000 hertz as a frequency. Ultrasound, but the frequency is too low for us to use in cardiology. So that's how that will be captured. Okay, so period and frequency are clumped together because they are reciprocals. Now the next 3 parameters are amplitude, power, and intensity. Those are the 3 different ways of describing the bigness of a wave. The good news for you is the physics component of your exam is simpler than the physics component of the cardiac sonographer's exam. So we don't have to differentiate amplitude, power, and intensity. We'll just call them the bigness parameters. So the intensity is the concentration of energy in a sound beam. It's the beam's power divided by the cross-sectional area. So it has units of watts per centimeter squared. The strength of the sound beam is determined initially by the ultrasound system. As sound travels, it gets weaker and weaker and weaker, and you can change the initial intensity of the sound beam. There's a knob on your machine called output power. And what you do by adjusting the output power is you change the initial level of intensity created by the transducer. The typical values have a very broad range of about 1/1000th to 100 watts per centimeter squared. Okay, so period and frequency are clumped together because they're reciprocals. The bigness parameters, call them the bigness, are clumped together because they're the bigness parameters. Now, why are these parameters on the left-hand side of the screen? Because they are all determined by the sound source. That's why. And this will be labeled on your notes. So all of these are determined by the sound source. So now we have 2 orphans. They live on the right-hand side of the screen, and they're crooked. They're wavelength and speed. So those parameters are on the right-hand side because they are the only parameters not determined by this source only. So let's talk about wavelength. Wavelength. Wavelength is the length of a single cycle. The analogy is, let's think of a wavelength as the length of a boxcar in a train. The length of one boxcar in a train, that's the wavelength, or one cycle in the train, as is illustrated by the double-sided red arrow in my cartoon. And it has units of distance, like millimeters. Now, the interesting thing, and the reason why wavelength is an orphan, is it is the only parameter determined by both the source and the medium. It's determined by both the source and the medium, and that's why it's an orphan. We can't change it, and it affects image quality. Now, some of you might be sitting there saying, wait a minute, that is the exact same cartoon you used to illustrate, period. And it is. But the difference are the units. You know, waves don't stand still, they move. So let's make believe we're on the side of a railroad track and a train goes by. The time that it takes one car to go by, that's a period, because it's a time. The length of one boxcar in the train, that's the wavelength, because it is a distance. So we're talking about one cycle, the time that it takes, that's the period, the length that it is, that is the wavelength. And higher frequencies give us shorter wavelengths. Now, everybody has to know this, because this is the basis of the most favorite question on any board exam, every ultrasound board exam. Everybody. I want you to know that 1 megahertz sound in soft tissue has a wavelength of 1.54 millimeters. Put a star next to that. The question you will get is, what is the wavelength of 2 megahertz sound in soft tissue? Or 3 megahertz sound in soft tissue? Or 5 megahertz sound in soft tissue? And all you do is take the 1.54 millimeters, divide it by the frequency in megahertz, and that's it. So, for example, 2 megahertz sound has a wavelength of 0.77 millimeters. 1.54 divided by 2. 3 megahertz sound has a wavelength of 0.5 millimeters. 1.54 divided by 1. So know that, and always pay attention to your units. They are millimeters. So that's just a standard question, and we should know that. On the first real ASC exam that counted, one of the questions on the boards, and that's before it was formal, you know, it was voluntary and all this, and I went, the test was given, I went and I was waiting outside, and the first question on the test was, what is the wavelength of 100 megahertz sound in soft tissue? That was the question. Sort of an irrelevant frequency, but the concept is very important, and everyone was frustrated, as you could imagine. Okay, so period and frequency are clumped together because they're reciprocals. The bigness parameters are the bigness parameters. They're all on the right-hand side of the screen because they're all determined by the sound source. Then we have one orphan, which is determined by both the source and the medium, which is the wavelength. And we have one more orphan, speed. So let's talk about that. The speed, of course, is how fast sound travels in a medium and has units of distance divided by time, like meters per second. This is determined by the medium only. Can we change it? No, because it's determined by the medium only. So the only time the speed can change is if sound is traveling in a different medium. If sound moves, for example, from blood to myocardium, the speed can change. But if sound is traveling in blood and continues to travel in blood, the speed will always be the same. And that's a miracle. That's a miracle. Here's an illustration of that. What do we have? We have 3 sound waves. 5 hertz, that's what is it? Oh, infrasound. 5,000 hertz, that's audible sound. 5 megahertz, that's ultrasound. Those 3 waves traveling in a block of gold. How long does it take those 3 waves to travel from the left block margin of the gold to the right margin? Well, you know what? The time is always the same, because all sound travels at the same speed through a given medium. The speed is about the medium only. Now, why is that a miracle? It's a miracle because we measure distance by time of flight. And that means that any single sound wave will have the same time of flight when it goes down to a certain depth and comes back, regardless of what its frequency is. And that's miraculous. If this didn't happen, we would not be here. All right? So that is an absolute miracle. All sound travels at a particular speed, and it never changes in that given medium. Now, there's something called soft tissue, again, which is a construct. You take muscle and blood and liver and you put it in a blender, and that's average tissue. And the speed of sound in soft tissue has a speed of 1,540 meters per second. 1.54 kilometers per second or 1.54 millimeters per microsecond. This, too, is a miracle. This means that sound travels 1 mile per second in the body. Put your fingers an inch apart. Sound travels this far in the body in 16 millionths of a second. Isn't that fabulous? Because sound boogies in the body, which means we have plenty of time to go down and come back, and go down and come back, and go down and come back. And that's the basis for real-time imaging. If sound didn't boogie in the body, no real-time imaging. Not a problem for people who want to scan livers, right? For the radiology folks, but for us, that would be a fatal flaw. So this is a real miracle. You should know the speed of sound in other media. Not really, but at least the ranking. The slowest air, then lung, then fat, then soft tissue, then tendon, then bone. So just know that order. And as a general rule, if you're stuck, sound travels slowest in gases, faster in liquids, and fastest in solids. This is a money slide. This slide has sort of become, it has its own life. What characteristics of a medium determine the speed of sound in that medium? What are they? Well, there are two. The density and the stiffness. Those are the two characteristics. So let's first describe what those things are and see how it affects the speed. So if I'm holding in my hands a ping pong ball and a marshmallow, and I squeeze them, different things happen. The ping pong ball retains its shape. It's stiff. The marshmallow squishes. That's stiffness, change in shape. If I hold in my hand two otherwise identical balls, one made of aluminum, one made of lead, both solid, which one weighs more? The lead. That goes to density. Things that are little and heavy are dense, things that are big and light are not dense. So those are different things, right? Stiffness goes to change in shape, density goes to weight. Those are different characteristics. Those are the characteristics that determine the speed of sound in a given medium. Now, how does that work? I know this sounds stupid, but patronize me, all righty? You know, it's like when you say to your kids, you'll thank me for this later. I want you to remember this. It's a favorite question on the boards. So just take out your thumbs. Watch this. Stiffness and speed. They start with the same letter, they go in the same direction. So when the stiffness is high, the speed is high. When the stiffness is low, the speed is low. What about density and speed? They start with different letters, they go in different directions. Well, that means when the density is low, the speed is going to be high. Or when the density is high, the speed is going to be low. So those of you that took your thumbs out don't have to study this anymore, because once you've done this once, you never forget it. Okay? So you're not going to get something like, what is the speed of sound in molybdenum? They're not going to do that, but they might say a medium is dense, is like stiff and not dense. Describe its speed. Well, if it's stiff, that's fast. If it's not dense, that's fast. So that means a medium that is stiff and not dense, that's our fastest medium. It happens to be bone. People get confused about bone. Of course, bone is stiff. Is bone dense? No, well, we hang around radiologists too many times. So they look at something and say, look at that density. They're not talking about weight, they're talking about X-ray absorption, right? Bone doesn't weigh very much, so it's stiff, it's not dense. That's why sound travels super fast in bone. So know this rule of thumbs, it will serve you well. Of the two of those characteristics of a medium, which one is more important? Generally, the stiffness is more important. And if that isn't in your notes, write that down. All right, so here's a chart. Charts are horrid, right? So what we're going to do is we're going to do the skinny. Now, I only have a few minutes, but I'll tell you this. Where does the skinny come from? The skinny comes from Randy Martin. Randy, past president of the American Society of Echo, good guy, lives in Atlanta. Say Randy's the funniest person I've ever met in my life. So when he'd have a physics question, my phone would ring. My phone would ring, I'd pick up the phone. Randy never introduced himself. And what he does, he picks up the phone, and what do I hear on the other side? He says, Rabbi, because that's what he calls me, Rabbi. And then he asks me a physics question, because from one of his fellows, and then he says, thanks, see you later, and he hangs up. But he said, give me the skinny. So here's the skinny. Watch this. Watch this. Period and frequency are clumped together because they are reciprocals, right? The bigness parameters are clumped together because they describe the same characteristic. All 5 of these are on the left-hand side of the screen because they're all determined by the sound source. Then we have 2 orphans. One orphan is determined by both the source and the medium, that's the wavelength, and the other orphan is determined by the medium only, and that is the speed. And the only parameter or parameters that the sonographer can change, the bigness parameters. So when you're done reviewing this once, you just use this architecture and it keeps everything organized well enough to answer most questions. So that's the skinny. And that's on page 6 of your notes, I believe. It's all written for you. Okay, so now let's talk about pulse sound. Because before we were talking about continuous wave. So now we're talking about this. Talking and listening. Transmit, receive. Talk, listen. On, off. So we have 2 parts to pulsed ultrasound. We have the talking time and then we have the listening time. Why do we care about this? Because if you want anatomy, you're using pulse sound. We have to use pulses because we have to use the go-return time or the time of flight to tell us the depth. So the only way to get an image of anatomy is with pulse sound. And the only use for continuous wave sound in cardiac ultrasound is what? Continuous wave Doppler, which does not give us an anatomic image, it only gives us a spectrum. So pulsed ultrasound has 5 additional descriptors. Guess what? There they are. And we'll see this again. So the parameters are, first, pulse duration. The actual time that the pulse is on. It has units of time and it's super short, like 3 microseconds. So transducers do this. Beep, beep, beep. The pulse is very, very, very short. That's the pulse duration. Now what I say is a pulse is a pulse is a pulse. The pulse never ever changes if you have a transducer in your hand. What changes is the time between the pulses when you change depth of view. If you're imaging shallow, you don't have to wait very long to send out the next pulse. So shallow imaging sounds like this. If you image deep, you have to wait longer for the reflections to come back. Deep imaging sounds like that. But the only thing we're adjusting is the listening time. The talking time remains constant. Now, if pulse duration is the time that a pulse exists, the spatial pulse length is the length of the pulse, the distance. It's as if we take a tape measure, hook the tip of our tape measure to the tip of the locomotive, drag it all the way to the end of the caboose, and measure that distance. It has units of distance, and it's determined by both the source and the medium. Well, that should make sense. If these are lengths, this length from there to there, that's a wavelength. And this wavelength, that's a wavelength. So in this case, the spatial pulse length is twice the wavelength. Well, if one wavelength is determined by both the source and the medium, 2 wavelengths are determined by both the source and the medium. Any length is determined by both the source and the medium. So the typical values are from 1/10 to 1 millimeter short. And short pulses make better images. And pulses that are short in time are short in distance. The pulse repetition period is the time from the start of a pulse to the start of the next pulse. And it has 2 parts, the talking time and the listening time. It's determined by the ultrasound machine, and we can change it. We change it when we change the depth of view. But what part do we change? We don't change this part because a pulse is a pulse is a pulse. We change only the listening time. And that's how the system listens for greater depths. Now this brings us to another big lie in ultrasound physics. Every time you see a pulsing pattern, you see that the talking time and the listening time have essentially the same order of magnitude. Big lie. Big lie. The listening time is like 100 to 1,000 times longer than the talking time. But of course you can't put that on a slide because the pulse will be on page 6 and the next pulse will be on page like 78, right? So understand that the listening time is much, 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 much longer than the talking time. So if we have Cartoon Man as an examiner, we might see something like this. 2 patterns. And the questions might be, can these patterns come from the same scan head? Well, the pulses are identical, so the answer would be yes. Whoops. What's the difference between the top and the bottom cartoon? How deep I image. And which one is imaging deeper? The one with the longer pulse repetition period, the upper cartoon represents deeper images. Now, what about this one? Can these signals come from the same scan head? No, because the pulses are different. So these have to be different scan heads. But what do I know about the imaging depth? Well, the pulse repetition period is the same for both of these. So the imaging depth is the same. So this would best be described as different transducers imaging to the same depth. So if Cartoon Man shows up, there you go. Different transducers. PRF. PRF is the number of pulses that occur in 1 second. So everybody listen. All of those had a PRF of 5 per second, 5 hertz. And this is where we want to break it down and make sure we use hertz. Because we'll say, okay, it's 5 hertz. 5 per second. What event are we talking about? The pulse. That's what we're talking about with PRF. Now, when we image shallow, the PRF sounds like this. High PRF. When we image deep, sounds like this. Low PRF. What determines the PRF? One thing and one thing only, how deep I image, and that's it. So that's the only thing that determines the PRF. So if I happen to have had a piano here and I hit different keys, let's see what it sounds like. Different frequencies, right? But all of these patterns had the same PRF. 3 hertz, 3 pulses per second. How many people get that? Good. Okay. So this is determined by the ultrasound machine, and you can change it. You change it when you change the depth of view. Now, the number of pulses a machine sends out in 1 second, it ranges from 1,000 to 10,000 hertz. 1,000 to 10,000 hertz. And what there is a tendency to do, but we're not going to do that, is say, oh, 1,000 hertz to 10,000 hertz, that's audible sound. No, 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 this is the PRF. So that means the ultrasound machine is sending out between 1,000 to 10,000 pulses per second, but the frequency of sound making up the pulse, that's ultrasonic. And that's why we are so anal about describing the word hertz the way we do. Because we don't want to think that this has to do with the frequency of the transducer. It doesn't. What does this have to do with, and only with, how deep I image? So that's PRF. Now, PRF stands for those 3 words, which I have decided I am not going to say. I haven't said them in 5 years. Okay? Anytime I see those words, I say, oh, that's the PRF. Because if I say this word right here, I'm afraid that I'm going to get messed up to think it's the frequency of the probe, right? So I just decided a long time ago that if I see that stuff, I say PRF, and I never say the F word. Okay. So pulse repetition period, pulse repetition frequency, they're reciprocals. Duty factor is simple. It's just the percentage of sound the ultrasound machine is talking. And I already told you that the system listens most of the time and talks just a little bit. So it's always a low number. It's always like less than 1%, and it's even lower when we go deeper. So listen to this. This is important. Shallow imaging, high PRF. High duty factor, high-ish percentage of time the machine's talking. Short pulse repetition period, short time from the start of one pulse to the start of the next pulse. Those things are synonyms. So you have a chart in your book that says, how can you describe shallow imaging? 4 different ways. How can you describe deep imaging? 4 different ways. Know that list. You have to ask the same questions over and over again. You test the same material, because basic physics is basic physics. So the examiners just have to figure out new, novel ways of asking the same question. So instead of saying with shallow imaging, what's the blah, 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 they say with a high PRF, what's the blah, blah, blah. Okay. So here is the second skinny. Everybody look. These guys are on the left-hand side of the screen because they were determined all by the sound source. Then we have one orphan that's on the right-hand side of the screen. It's a length, so it's determined by both the source and the medium. These guys describe the pulse only. The time, the length. They never change because a pulse is a pulse is a pulse with one scan hit. And these guys are the ones that include the on time and the off time. So those are the ones that change when we change the depth of view. So those are the ones that we change. And if you can go over the notes sort of briefly and hook onto the skinny, you're going to get a C at least on your physics stuff. Okay. And you can distinguish yourself brilliantly on your physics portion of your exam. It's not going to change your score one bit, because it's like having a 1-credit course in college. You're not going to graduate magna cum laude because of that. So we understand where we have to invest our time. Super important, the range equation. Ultrasound machines measure distance by the pulse's time of flight, or the go-return time. If a transducer sends out a pulse and a reflection comes back very, very fast, then the reflecting boundary is shallow. If the pulse does this, then the reflector is deep, because the go-return time is directly related to how deep the reflector is. I want you to know the 13 microsecond rule. For every 13 millionths of a second that transpire in time of flight, the reflector is 1 centimeter deeper in the body. So if I have a reflecting boundary that's 1 centimeter deep, the go-return time, 13 microseconds. 2 centimeters deep, 26 microseconds. 3 centimeters deep, 39 microseconds. So that's how ultrasound machines measure distance, by dividing seconds into billionths of parts. We can be a little bit more practical now. Let's talk about resolution. Resolution is the ability to accurately image, and there are all kinds. The first is actual resolution. I have to say this, anyone who's taking pictures, please refrain from taking pictures, and if you have pictures on your camera, please delete them. Thank you. All right, the first is axial resolution. The question that's answered is, if two structures are close together, one in front of the other, do I see them as two separate blips? That would be good. Or do I see them as a blob? So axial resolution tells us how accurate our picture is when reflectors are one in front of the other. And it has units of distance. And it is equal to our old friend, the spatial pulse length divided by 2, which means the shorter the pulse, the lower the number, the better the picture. So this is like golf. You want a low number. Now let me explain why a short pulse gives us better axial resolution. If I am Sidney Scanhead and I send a pulse out in this direction, there are like 9 reflectors in a row. So if I send out a pulse, beep, what do I get back? Beep, 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 beep. That's accurate. If I send out a long pulse, hello, what do I get back? Hello, low, 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 big long blob. Why? Because the first reflection didn't come back in its entirety before the second or the third or the fourth. So we want a short pulse. How do we make a short pulse? Well, we make a short pulse because transducers are designed to make short pulses. They have something called a backing material which stops the crystal from ringing, something like this. And that short pulse makes for better axial resolution. Now, since a pulse is a pulse is a pulse, the axial resolution is the same everywhere on my image, and I can't change it. All right? And the typical values from about 5/100th to 5/10th of a millimeter. So here's the story with axial resolution. The top train, the train is long. I have 3 cars in my train. I have 1, 2, 3 cycles in my pulse. The pulse is long. My axial resolution is poor. So what do? I put down that transducer and I pick up a transducer that creates the second pulsing pattern. Here, this has 1, 2 cars in the pulse. So the pulse is shorter. All right? So that's an example of less ringing. Not letting that transducer ring and ring and ring. What about here? Here I have 1, 2, 3 cars in my train. Here I have 1, 2, 3 cars in my train. But this train is shorter because each car is shorter. And a short car means a short wavelength. What kind of frequencies give us short wavelengths? High frequencies. So this is why high frequencies give us more accurate pictures. Because they make shorter pulses and improve my axial resolution. All right. Now, of course, then I would say if I was an extremist, well, I want to use 100 megahertz sound. Well, I can't do that because high frequencies attenuate, so I can't penetrate with them. So sort of the party line is you want to use the highest frequency you can that reaches the clinical area of interest, because then you can reach it and then you get the best picture from it. The next resolution is lateral resolution. Lateral resolution distinguishes structures that are side by side or perpendicular to the beam's main axis. And it depends upon beam diameter. And a beam looks like an hourglass. So since beam diameter changes with depth, lateral resolution changes with depth. Where is it the best? Where the beam is the narrowest, that's called the focus. Okay? That's called a focus. So if we have 5 sets of pins in a phantom, 1, 2, 3, 4, 5, and I scan them, and these are the images that are created, we'll say, where is the focal point? It is at D, because D is the most accurate representation of the pins of the phantom. What is the lateral resolution at depth B? It's the width of that horizontal line. What's the lateral resolution at depth A? It's the width of that line. And the width of those lines represents what? It represents the beam diameter at that depth. And you will notice on your scans that when you go real deep, all of a sudden points end up becoming horizontal lines. So you want to remember to call this point spread artifact. That's a term that's used in the cardiac community that you want to know about, or beam width variation. Okay? Those are the terms, and that's what we're talking about. Other kinds of resolution. Contrast resolution. That's simple. That's just grayscale. The image on the left has poor contrast resolution. The image on the right, good contrast resolution. Spatial resolution. Spatial resolution is crazy. It's a combination of everything. It's a combination of axial resolution and lateral resolution and gaps between lines and the characteristics of our monitor. So it's detail. It's just a smorgasbord of things. All right? That's called spatial resolution. But now, let's talk about temporal resolution. Temporal resolution asks the question, if something is moving, do I know where it is? And in order to know where it is at every instant in time, what do I need? A high frame rate. That's what I need, a high frame rate. Because if I have a low frame rate, I'm going to look like an old Charlie Chaplin movie. That herky-jerky thing. So temporal resolution is simply equal to the frame rate. The frame rate, typical ultrasound machines, between 20 and 100 hertz. Aha, between 20 and 100 events. What is the event? The picture. A finesse question might be this. What's the fundamental limitation of temporal resolution? And you have, the answers are 2. Propagation speed and depth. Those are the 2 things that really determine temporal resolution. But what's the fundamental limitation of temporal resolution? It's the speed. If sound doesn't boogie in the body, there's no way you're going to have a high frame rate. Right? It's not happening. That's why it's a miracle that sound travels a mile per second in soft tissue. It's astounding. So, this is the fundamental limitation. Thankfully, not much of a limitation. So what do I have? The image on the left, we see our mitral valve leaflets. They're moving pretty fast. We see where they are at every instant in time. I have good temporal resolution because I have a high frame rate. The loop on the right, I have a low frame rate. I have a herky-jerky picture. So those would be differences in temporal resolution. We'll talk about more of this with color. All right, now there are 4 sort of user-adjustable controls that change the frame rates, and we have to know about them. They're going to be especially important when we do color, so this has 2 purposes. So the first control, depth of view. Shallow imaging looks like this, and deep imaging looks like this. Well, which image is made quicker? The shallow image. So shallow imaging means I make a frame quicker, my frame rate's higher. Of course, we always have to reach our clinical region of interest, but that doesn't mean we can't change the view to make it closer to the transducer. Or alternatively, use transesophageal echo and move the mountain to Muhammad, right? By moving the transducer right up next to our anatomy. Now, the other 3 factors are all about the number of pulses per frame. Single or multifocus. Single focus looks like that. Multifocus looks like this. If I have 5 focal points, I need 5 pulses. So which one makes a quicker frame? Single focus. Which one makes a better image? Multifocus. So you're not going to have a question that says, does single focus improve resolution? Because the answer is yes and no. It gives you a higher frame rate, but the image isn't as good. We control this. Sector size. We can have a wide sector or a narrow sector. That's a narrow sector. That's a wide sector. Well, the narrow sector uses fewer pulses, takes less time, has a higher frame rate. Improved temporal resolution. Now you notice here that the spacing between the lines is unchanged. That's a subtlety. We don't really see the line spacing. But there actually is a control that does that. So what happens when we change the line spacing? Well, if I have this, it doesn't take very long to make a picture. So my frame rate is high, but my detail is terrible. What about this? Here, my spatial resolution is excellent, but my frame rate is low. Now, we generally don't see this. This is set up in the presets because the manufacturers don't want us to do this because they want us to do this because they know that if we do this, we're going to blame them. So they hide this from us. But understand these 4 settings. Why? Because when we talk about color Doppler, it is critical. Color takes so many pulses that it's critical to image, to have our color box as shallow as it can be and as narrow as it can be to save time. Otherwise, we will have horribly slow frame rates and will miss short duration events. So this has 2 places to be tested. So again, nice little list. You get higher frame rates when you image shallow with a single focus and a narrow sector and a low line density. You have a lower frame rate when you image deep with a multifocus and a wide sector and a high line density. Now for us, of course, since most of the time we're looking at things that are dynamic, we need a reasonably high frame rate. If we're looking at an aorta, for example, we can live with lower frame rates and a little bit more data. Highest frame rates, what's the highest frame rate? M mode, right? Every pulse is an image. So M mode has the highest temporal resolution. Okay, so I stop here because my 45 minutes is up, and I'll come back and I'll do Doppler, but I think that my time is up.